Okay, part 3 of chapter 11 here starts off with a summary from the differences between the primary immune response seen here on the left and the secondary immune response on the right. And I'll just let you look through that. What you might find on the next exam is just a compare and contrast between primary and secondary. Or, if I want to be easy and not have a handwritten question, essay type question, it might be a set of matching. Alright, 11.14 looks at how some types of vaccines can be created using less pathogenic organisms. So here there are two viruses depicted. You've got cowpox and smallpox. These two viruses are very closely related, but cowpox, as you might imagine, infects cows. Smallpox, you all know, infects humans. And it was found in the time of Jenner that milkmaids would often come down with basically smallpox of the hands, all right? Because the milkmaids, those who were milking cows, would get the cowpox virus on them, and that would cause pox or pox, wart-like lesions on their hands. And then it was also noticed that when smallpox went through the farm or the people there, that those milkmaids never came down with smallpox, so they were protected. And Jenner noticed this, and what he did was he actually ground up the scabs from individuals who had a very mild case of smallpox, and then intentionally inoculated it to individuals as the process of vaccinia, or vaccination, coming from the word vaccinia, which is the cowpox, the official name of the cowpox virus. And this would then give a small, because it was the scab was from a very weak disease patient. Those who got the dried up scab material usually came down with the mild form of the disease. All right, but in that instance, 1% actually came down with full-blown smallpox and then died from it. But that's actually much better than getting just smallpox when it went through in an outbreak, because generally at that point in time, about 25% of people would die. And so 1% versus 25%, which would you take? All right, definitely the 1%, but you wouldn't want your kid or you to be that 1%. All right, so how this works is with the cowpox, you've got the green, red, and blue antigen, and the smallpox virus, because they are closely related, have the blue, the green, and then the black epitope antigen. And so if a person was infected with cowpox, then he or she would make antibodies, the blue, the red, and the green antibodies. And then if they were infected with smallpox, well, then the blue here, and the green antibodies would be protective. The red weren't, but as long as you had the blue and the green, didn't matter about the black here, that those patients were protected. And this is called shared antigenic determinant, and this is still a technique that is utilized today. All right, then how are vaccines made? All right, usually they're going to be killed or inactivated viruses, killed or attenuated. And how this is done is typically the virus is allowed to grow in cells, tissue culture cells in the lab, and sometimes just adding virus to human cultured cells would could cause the virus to mutate. All right, so that's one way, taking it out of the human host from the patient, grow it in the human cultured cells, and it's just enough of a change that it would cause mutations. All right, and those mutations generally are not more pathogenic as what you might see in movies, but rather make it less pathogenic. Another way of decreasing the virulence of a pathogen, of a virus here, is to, after it's cultured in human cells, then to culture it in a different type of cell. All right, so this would be monkey cells. And really it's where this happens is that over time, then the virus will begin to undergo mutations. And so then you've got now this blue and yellow virus. And so then it can get transferred back to the human cells. But now you've changed enough of the virus that it actually prefers the monkey cells. All right, actually binding here, remember this is a virus, so it needs that particular interaction between the host cell receptor and the ligand on the virus. And now through many, many passages, all right, putting it into the cell and having it come out. So this process here is one passage. Over here would be a second passage, a third passage, even though this could be like 300 times. All right, now you put it back in the human cell, cultured cells here, and the virion doesn't infect. All right, but it's still similar to the blue guy, sort of. All right, it doesn't look that way from this picture, but it is. And so now this can be injected into a person for the purposes of vaccination and not cause disease. All right, then how to make vaccines with toxins or some bacteria. Sometimes polysaccharides don't make a good immune response, or sometimes part of it is not antigenic, so to speak. Right? It doesn't really elicit a good response. But what scientists can do is actually combine pieces, and now you have a polysaccharide toxoid vaccine. So this is a conjugate of a polysaccharide and the toxin. And both of these pieces can then be internalized. And it's not really the polysaccharide that you want to make an immune response, but rather this toxoid. And sometimes it's hard for the toxoid to get pulled into the cell, but if it's attached to the polysaccharide, that gets pulled in easily, and then everything here gets degraded. And then by luck, over time, you end up having a piece of the toxoid get presented, and that will induce an immune response specific to the toxoid. All right, so you create conjugates. One part is true material to make the vaccine against. One is kind of not like a decoy, but an enticer for the immune system to pull it in and respond against. And then it just happens to respond against the toxoid, which you want. All right, conjugate vaccines enable high affinity antibodies to be made. All right, so this process continues to go on, and you end up allowing this B cell, this plasma cell, to make antibodies that will then bind the polysaccharide, and you also have the toxoid part here that eventually one of these B cells will pick up on and respond against that. Alright, so I mentioned this in class just a little bit in terms of looking at the original antigenic sin, and that mechanism of how the influenza virus can mutate. Right, the influenza virus is always changing because it has a very high mutation rate, and That is why it's necessary, important to get a vaccine every year. All right, because the flu virus can actually mutate very quickly, and what was here in June might actually really not be the same thing that gets there in November. All right, so this is looking at the H1N1, the swine flu, that first came onto the scene in 2009, early 2009, and so that's when this came in, and it was actually quite problematic for populations. A lot of people were dying from it, and then probably the CDC and WHO got involved, and in 2009 of June of 2009, the vaccine production was started. And in the summer months, actually, all right, you had a very high rate of increase in the pandemic influenza peak, right, where it moved from Asia, where it originated, and spread across, I think, nearly all continents. And in October 2009, pandemic peak, all right, many deaths occurred because of H1N1. And here you had vaccine delivery, all right, how the vaccine is slowly given to some people, and then you have increased use where they can see that it's starting to be effective. And right here you start seeing a decline in the cases as the vaccine rate goes up, and then towards the end of the year, very few cases. And you know, this was 10 years ago, so you guys were still young. I don't know if you remember this, but this was actually the year that my son was born. And not that I am a germ phobe or anything like that, but this actually did worry me, all right, because who were at risk? The elderly and infants. And I had an infant born right here, all right, and I actually kept him out of organized daycare, all right, because I didn't want to run the risk of him coming into contact with that influenza. All right, is that influenza still a problem? Yes. Go figure, my son's friend came down with it last week, and both he and my daughter came home and said, hey, Calvin's got the swine flu. I'm like, oh, that's awesome. All right, nerd-wise, he's fine. So it's still around, but there's vaccines available for it, and if you had protection against H1N1, all right, H1N1, as long as it hasn't mutated too much, it's still out there, probably in the original form, and so you would be protected. My son's friend who did get influenza last week did not get his flu vaccine earlier this year or end of last year, so always get your flu vaccine. And this concludes Chapter 11.